Today we are going to discuss step functions, how you can use step functions to build piecewise continuous functions, and how those functions transform and back transform. So let's start out by remembering that UA of t is a function that's 0 when t is less than a and is 1 when t is greater than or equal to a. Here's what the graph looks like. You can see that there's a jump discontinuity when t equals a. A special function I want to make sure you know about is u of t, which is essentially u0 of t. So the jump happens when t equals 0. And this is often used instead of UA of t. One writes u of t minus a. And the point here is that this thing jumps when this thing is 0. So when t is less than a, it's 0. And it's 1 when t is greater than a. So UA of t and u of t minus a are exactly the same. And sometimes it's notated this way. U has another name sometimes. And very often you'll see u of t written as h of t, and the h stands for Heaviside, who developed a lot of what we're talking about today, and the function's named after him. So h of t minus a is exactly the same as UA of t. Okay, so let's take a look at Laplace transforms. We know already from previous work that the Laplace transform of UA of t is e to the minus sa over s. And what we want to now do is figure out how do we transform a function times a step function. Well, it turns out the right thing to do is to try and transform the step function times f not of t, but of t minus a, and we will see how that works out when we actually do the transform. Okay, so that's exactly the same as writing u of t minus a, f of t minus a, or h of t minus a, f of t minus a. Okay, so let's go ahead and try and transform this thing. Laplace transform of UA of t times f of t minus a is the integral from 0 to infinity, UA of t, f of t minus a, times e to the minus st dt. And of course the point here is that this thing is 0 between 0 and a, so we just get 0 for that piece of the integral. And then when t equals a, this is 1, and we've got this. Now we want to make this look like a Laplace transform, and it doesn't, and the reason it doesn't is actually twofold. Number one, this limit needs to be a 0. And number two, that needs to be t. So we need to transform this, and we do this by making the change of variables capital T is t minus a. And that means that d cap t is little dt. And here that's going to give us that little t is t plus a. How do the limits transform? When little t is a, t is 0. And when little t goes to infinity, so does big T, because it's just little t minus a. So the integral that we have transforms to integral from 0 to infinity f of capital T e to the minus s. Now remember that little t is t plus a, so we just shove that in there. And now notice this is e to the minus s cap t, e to the minus sa, and we just factor that e to the minus sa out of the integral. And what you can see here is this is the Laplace transform of the function f. Okay, it's just with the dummy variable cap t replacing the variable little t, but it integrates out of the problem. So we end up with e to the minus sa times f of s, and that's our formula. So the Laplace transform of UA of t, f of t minus a, is e to the minus sa times cap f of s, where cap f is the transform of little f. So this formula is easy to use for back transforming. So let's look at e to the minus 3s times 1 over s minus 2. Now the inverse transform of 1 over s minus 2 is e to the 2t, and that's the thing playing the role of f up here, okay? It's the inverse transform of cap f, which we're taking to be 1 over s minus 2. So according to the rules here, the Laplace transform of e to the minus 3s times 1 over s minus 2 needs to be u3 of t times f of t minus 3, and you'll remember that f of t is e to the 2t, so we get u3 of t e to the 2 t minus 3. Now forward transforming is harder, and the reason it is we have to figure out a way to write our t function in the form ua of t f of t minus a. We can't write it as f of t. So as an example, let's transform u2 of t times 3t plus 4. For this to work, we need to write 3t plus 4 as a function of t minus 2 because of the u2 of t part here. So 3t plus 4 can be written as 3t minus 6 plus 4. And the reason we do that is now I can write this as 3t minus 2 plus 10. So f of t minus 2 is 3t plus 4 when f of t is 3t plus 10. So that's what's going to get forward transformed. So u2 of t times 3t plus 4 is going to transform to e to the minus 2s, and now times the Laplace transform of f, which is 3 over s squared plus 10 over s. Now, there's a general method for finding such a function. So suppose that we have ua of t times g of t, and we want to rewrite that as ua of t times f of t minus a, because that's what we need it to look like to forward transform it. So what we do is we let f of t be g of t plus a. So in other words, we just shove a t plus a into g. And what you can see then is that f of t minus a is going to be g of t minus a plus a, which is g of t. So if we use this definition for f, we're going to get f of t minus a to equal g of t. So taking a look at our previous example, u2 of t times 3t plus 4. So g of t is this 3t plus 4. So what we do is put a t plus 2 in every place that we see a t. And what that gives us is 3t plus 2 plus 4, which is 3t plus 10, which is exactly the function we found before. Okay, so another example. Let's Laplace transform u pi of t times cosine t. So again, g of t is cosine t. We need an f so that this is actually f of t minus pi. So what we pick for f of t is g of t plus pi. The cosine of t plus pi, well, that's t plus halfway around, which is minus the cosine of t. So u pi of t cosine of t can be written as u pi of t minus the cosine of t minus pi. And that means that the transform is going to be e to the minus st times the transform of f, which you remember is minus cosine t, which gives you a minus s over s squared plus 1. Okay, now what we're going to do is talk a little bit about why you might care about step functions. And the answer turns out to be, how do we write piecewise defined functions without having to do multiple integrals and break things up into various pieces and such? Okay, so as an example, let's take g of t to be t when t is less than 2. We'll have it be 2 when 2 is between t and 3. And we'll have it be 0 when 3 is less than t. And you can see this is what the function looks like. That's g of t equals t all the way up to t equals 2. At this point, the function value is 2, and it stays 2 until we get to 3. And then at 3, it jumps back to 0. Now, how are we going to do this? Well, the answer is step functions will do this for us. And I want to look first at 1 minus u2 of t. And what you'll notice is that's really, the u2 of t comes to us because we want to change what's going on at 2. Now, if you look at 1 minus u2 of t, it's 1, or if you want to think about it this way, on, until t equals 2, in which case u2 of t turns on and you get 1 minus 1, which is 0. So this whole mess is now off for t bigger than 2. Now this interval right here, let's look at u2 of t minus u3 of t. Well, that's off, or 0, when t is less than 2 because both of these things are off. It's 1, or on, when 2 is less than or equal to t is less than 3, because then u2 of t is on, or 1, but u3 of t is 0 or off. And then suddenly when we hit 3, this turns on. 1 minus 1 is 0, so this whole mess is 0. Okay, so let's look at what happens here. So we build g of t as t times 1 minus u2 of t, which is going to give us a t as long as t is less than 2, but then this is 0. At this point, this thing, u2 of t minus u3 of t, turns on because it's when t crosses 2. This is 1 minus 0, or 1. So 1 times 2. So we're now at 2 when t is between 2 and 3. And then when t equals 3, we get 1 minus 1, or 0, and this is off. So the net effect is we've gotten exactly what we're supposed to get. We get a t between 0 and 2, we get a 2 between 2 and 3, and we get a 0 afterwards. Okay, now we're going to transform this thing. And the way we're going to do that is we're just going to multiply things out and collect terms. So we do that, and we collect the u2 stuff, and we get a 2 minus t times the u2. We get a minus 2 times the u3, and this is the stuff that's not multiplied by any step function. This is going to be easy to transform. This is going to be easy to transform because it's in our table. This is the part where we have a function times u2 of t. Now, as you'll recall, what we want to do is figure out how to write this function 2 minus t as a function of t minus 2. And we want to write it this way. And remember, the trick here is to go in and look at this function and put in a t plus 2 every place you see a t. And when you do that, you get f of t, which ends up being minus t. Okay, so 2 minus t, u2 of t, is going to transform as e to the minus 2s times the transform of minus t, which is minus 1 over s squared. And now when you collect everything, Laplace transform of t is 1 minus s squared. The Laplace transform of this piece we just calculated is minus 1 over s squared times e to the minus 2s. And then the Laplace transform of 2 u3 of t is the minus 2, and then the transform of u3 of t is e to the minus 3s over s. And we have the transform of the entire function.